Hi everyone, this is Maverick Paul, the Chemistry Guru. Now in this video, we want to run through the suggested solutions for 2022 A-Levels H2 Chemistry Paper 1. So let's take a look at question 1. Now question 1, mass of 1 mole of each of 4 compounds is shown. We have 2 compounds here, where if you look at the mass of 1 mole of compound, which is my molar mass, they are very close. Which row is correct? Comparing lowest boiling point all the way to highest boiling point. So the topic tested in this question will be under chemical bonding, and involving chemical bonding, what we will have to do first is to first thing identify what type of substance each of these compound is, and we identify what is the type of attraction that we need to overcome during boiling each of these substances. So each of these compound, let us take a look at that. First guy is sodium fluoride. Sodium fluoride obviously is an ionic compound. If it is an ionic compound, then we will expect strong ionic bonds between the ions, and the boiling point in this case as compared to the rest of the compounds which are simple molecule is expected to be the highest, and definitely we will expect your sodium fluoride to have the highest boiling point. Then involving the rest of the molecules, CH3CH2CH3, CH3CH2NH2, CH3CH2OH, all of them are simple molecules, and since they're simple molecules, we will expect weak forces of attraction between the molecule. We will expect the boiling point to be significantly lower, and in this case, we will be able to eliminate option B, where sodium fluoride, it is not the highest boiling point. So B, in this case, will be eliminated. Now, the next thing we will have to do is we will have to compare the specific type of intermolecular force for my simple molecule. Then we can do comparison involving which one of them has a higher boiling point, which one of them has a lower boiling point. One thing to note is when we compare the different types of intermolecular forces involving hydrogen bond versus permanent dipole interaction versus instantaneous dipole, induced dipole interaction, we have to make sure that we're comparing molecules with similar size. That means their molar mass has to be similar, and we have similar electron cloud size. Then this comparison, where hydrogen bond is stronger than permanent dipole interaction, which is in turn stronger than instantaneous dipole, induced dipole interaction, then this comparison will be valid. So we know that this is valid because if I compare the molar mass for the 3 simple molecules, all of them is roughly about 40 something. This will mean that yes, I will have similar size, involving electron cloud size are similar, then we can safely compare hydrogen bond stronger than PD-PD, stronger than ID-ID. The next thing that we'll have to do, of course, is to identify for each of these simple molecule, what is the specific type of intermolecular force. Now, involving CH3CH2CH3, which is a hydrocarbon, we know that hydrocarbon, carbon bond is nonpolar, carbon-hydrogen bond is also nonpolar. This molecule will be nonpolar. I'll expect the dominant intermolecular force for CH3CH2CH3 to be weak ID-ID attraction for nonpolar molecules, and we will expect the boiling point for CH3CH2CH3 to be the lowest. And in this case, what we will be able to do is we will be able to eliminate option D. And how about my remaining 2 molecules involving CH3CH2NH2 and CH3CH2OH? Now you notice the amine has an NH bond, and therefore it should be able to form hydrogen bond between molecules. Involving my alcohol, because of the OH bond, you will also be able to form hydrogen bond between molecules. So now the comparison will be between hydrogen bond versus hydrogen bond for my amine versus alcohol. Which one will have a higher boiling point? Which one has a lower boiling point? The factors affecting hydrogen bond is here. I have 2 factors affecting hydrogen bond. The first one is the extensiveness of my hydrogen bond. In general, if I have a molecule that can form more extensive hydrogen bond with other neighbors, then we will need to bring more hydrogen bonds per molecule. Energy required for me to separate your molecule will be greater, and therefore it will cause the boiling point to be higher. And most of the time, if there's a difference in extensiveness, we will focus on that. That is the dominant factor that we will consider. If I have more extensive hydrogen bond, then the boiling point will be higher. Now the second factor comes in when the extensiveness is the same. If I have the same extensiveness, then if I consider a molecule that contains HF bond versus molecules that contains HO bond versus molecules that contain HN bond, since HF bond is more polar than HO bond and HN bond. If I have a molecule that contains HF bond, the hydrogen bond between those molecules will be stronger as compared to molecules that contains HO bond, which in turn will be stronger than molecules that contain HN bond. So we will have to consider these two factors, extensiveness versus polarity, which one is relevant if I compare my CH3CH2NH2 versus CH3CH2OH. The first thing we do is we compare extensiveness, and you notice what we have here is if I try to draw all the possible hydrogen bonds each of these molecules can form, involving amine functional group, nitrogen has a lone pair. I can form one hydrogen bond with a neighbor. I have two NH bonds. Each one of them can form hydrogen bond with two other neighbors. Maximum number of hydrogen bond that your amine can form will be 3 hydrogen bonds. Involving my alcohol, each oxygen has 2 lone pair, and the oxygen has 1 OH bond. Total number of hydrogen bond your alcohol can form will also be 3 hydrogen bonds per molecule. And since both of them can form the same number of hydrogen bond per molecule, the extensiveness is the same. So extensiveness will not be the important factor here. I'll have to compare polarity. So the next thing comes in will be my polarity. If I compare my OH bond in my alcohol versus NH bond in amine, OH bond is more polar because oxygen is more electronegative than nitrogen, which is in turn more electronegative than hydrogen. So OH bond is more polar, and we will expect oxygen to be a bigger partial minus charge, hydrogen will be a bigger partial positive charge, whereas involving NH bond, since the difference in electronegativity is smaller, nitrogen will be a smaller partial minus, hydrogen will be a smaller partial plus, and because of that, when I consider hydrogen bond, the intermolecular interaction, the hydrogen bond between alcohols will be stronger because I have a more positive hydrogen attracting a more negative oxygen. This hydrogen bond between alcohols will be stronger, and if I consider your intermolecular interaction, your hydrogen bond between your amine will be weaker because I'll have a smaller partial positive hydrogen attracting a smaller partial negative nitrogen. And the conclusion will be, I'll expect alcohol intermolecular interaction or the hydrogen bond between alcohol molecules to be stronger. Boiling point for alcohol will be higher than boiling point for amine. So because of that, we can eliminate option A. So finally, after all this comparison, we will be able to come back to this list. Sodium fluoride will have the highest boiling point because it is an ionic compound. Propane, which is a hydrocarbon, will have the lowest boiling point because it is nonpolar. We have the weakest ID-ID attraction between molecules. Comparing amine versus alcohol, alcohol will have stronger hydrogen bond between molecules because OH bond is more polar than NH bond, and therefore the answer to question 1 will be option C. Now let us move on to question 2. Question 2, in the interhalogen compound BrCl, there's a single covalent bond which is polar. Which statement helps to explain the polarity of the BrCl covalent bond? We have 4 options, A, B, C, D, and we will try to look through each one of them and see which one can explain why your BrCl bond it is polar, and which is the delta plus and who is the delta minus. Now, the concept tested in this question actually is under atomic structure, and in general, you should be able to explain why this bond is polar, because if I consider bromine bonded to Cl, chlorine is more electronegative than bromine, and if it is more electronegative than bromine, chlorine will be able to pull the electron pair closer to itself. Consequence involving that, Cl is going to be a partial minus charge, your bromine will be a partial positive charge. So because of that, we will expect the bond to be polar. Bromine is a delta plus, Cl it is a delta minus. Now if I run through my options A, B, C, D, let us see which one is the most relevant one. Involving A, bromine more electronegative than fluorine, this is definitely not true. So we will reject this straight away. Involving B, outer shell electronic configuration of both elements is S2p5. Now this is true, but it actually doesn't really explain why chlorine is more electronegative than bromine. It is true, but not really relevant. So let us see whether we have a better answer. Involving C, what we have is the outer shell electrons are more shielded from the nuclear charge in bromine than they are in chlorine. So we actually have to try to go a little bit deeper to try to understand what do we mean by outer shell electrons are more shielded from the nuclear charge in bromine versus in Cl. Now, chlorine is in period 3. That means you have 3 electron shells. bromine is imperial 4, so therefore we have 4 electron shells. And what I've done is I'm using the Bohr's model, which is easier for us to visualize, looking at the number of inner shells that each of these halogen will have. Now bromine, if it is imperial 4, valence electron is in n equals to 4, then I'll have 3 inner shells. And remember, my inner shells will be able to act as an effective shield to block the attraction between the nucleus and my valence electron. If I compare this with chlorine, chlorine is imperial 3. That means my valence electrons, they are in the third principal quantum shell. I'll have 2 inner shells that will act as an effective shield, blocking the attraction between the nucleus and my valence electron. So comparing these two guys, what we will expect is involving bromine, because I'll have more inner shells, then there will be greater shielding effect, and the overall effective nuclear charge will decrease, overall attraction between the nucleus and the valence electron will decrease, and this will mean that the bromine is less electronegative. Conversely, if I consider our chlorine, less inner shell, less shielding effect, I will have greater effective nuclear charge. The nucleus will be able to attract the valence electrons more strongly, causes this guy to be more electronegative. So you notice involving our conclusion that we have for statement C, it is able to explain how come chlorine is more electronegative than bromine. So therefore C, in this case, will be my best answer. Now statement D, the repulsion between electrons in the outer shell is greater in bromine than it is in chlorine. This statement is false, because for bromine with a bigger period and a higher principal quantum number, then we will expect the valence electrons to be in a bigger and more diffuse orbitals. So therefore, this will mean that the repulsion between electrons, actually there will be less repulsion between my electrons. So statement D in this case is false, and this is not true. So in this case, answer to question 2 will be option C. Now question 3, we have thioacetic acid and ethanoic acid, both act as weak acids in solution. pKa for both acids are given. pKa for thioacetic acid, which is 3.33, versus ethanoic acid, which is 4.76. Actually, based on the pKa values, we will know that thioacetic acid, since it has a smaller pKa value, it is going to be more acidic. Ethanoic acid actually turns out to be less acidic than the first acid. Involving each of these statements, we want to decide which is the correct statement. So the topic tested in this question, since it is comparing pKa values and comparing acidity, then we know that, okay, this is related to ionic equilibria. And as mentioned previously, I'll expect the first acid, my thioacetic acid, since it has a smaller pKa value, the Ka value is larger, it is a stronger acid, it will be able to dissociate to give me more H+. Whereas if I consider my ethanoic acid, since it has a bigger pKa value, Ka is smaller, it is a weaker acid, it will donate H+ less readily. So with this in mind, let us consider each of these options. Statement 1, H+, more easily removed from ethanoic acid because OH bond is more polar than SH bond. Now, if you look at the first portion, straight away this is not true, because we have already concluded based on the pKa value that my ethanoic acid, it is a weaker acid. So comparing the tendency to dissociate and to donate H+, we will expect ethanoic acid to be a weaker acid, and it should be harder to release H+. So H+ should be less easily removed from ethanoic acid. Statement number 1 is not true, so it's not what we want. Involving statement 2, Ka value is larger for ethanoic acid. Again, once we take note of this first portion, which is already wrong, it is a weaker acid, Ka value for ethanoic acid is supposed to be smaller. Straight away we can reject, and whatever that comes after that is actually not relevant. It is not important, because the first statement itself, it is already false. So statement number 2 is also not the answer. Number 3, what we have is in 2 solutions of the same concentration, thioacetic acid will have a smaller pH because SH bond is weaker than my OH bond. First portion is okay. Involving thioacetic acid will have a lower pH. Since it is the stronger acid, we will expect this guy to be able to dissociate more, to give me more H+. Of course, when we compare pH, we have to compare same concentration of both acids, then it is a better comparison. If the concentration it is the same, then a stronger acid will dissociate more to give me a higher concentration of H+, which will also lead to a lower pH. So statement number 3 is valid. Statement number 3 is correct. So based on all my 3 statements, only number 3 is valid. number 1 and number 2 is totally wrong. Answer to question 3 will be D. Now question 4, we have this gas is an equimolar mixture of O2 and N2O. Which mass of N2O is used to make 5 dm³ of ethanox measured at a certain pressure, stored at a certain temperature. Now, if you are given all this information, we roughly know that, oh, this topic tested will be involving gaseous state. And what I need to do is I just need to use the ideal gas equation for some calculation, keeping in mind this is an equimolar mixture of oxygen and N2O. First thing we have to do is we have to substitute everything into my ideal gas equation to find the number of mole of this ethanox. Remember, if I consider my pressure has to be in Pascal, which is already given in the question. Volume has to be in meter cube, so we will convert 5 dm³ to meter cube. Temperature has to be in Kelvin. Everything must be in SI unit, right? Everything must be under SI unit. Temperature will be 293 Kelvin, and therefore I can substitute everything into my ideal gas equation. PV equals to nRT. I write this in terms of number of mole of that gas equals to PV divided by RT. Pressure, we can sub in the value. Volume, I can sub in the volume, 5 times 10 to the power of minus 3. R is 8.31, gas constant. Temperature is 293. So what we can do is we can calculate this. Number of mole of your ethanox gas is 72.90 moles. So once we have that, and question did tell me that your ethanox gas, it is an equimolar mixture of O2 and NO2, which means that the number of moles of these two guys are the same. So mole of N2O will be whatever that we've determined previously divided by 2, 36.45 moles. Once we have the number of mole, all we need to do now is we multiply the number of mole by the molar mass for N2O, and I'll be able to determine the mass of your N2O, 1604 gram. So once we have that, the options A, B, C, D, it is given in terms of kg. Obviously, the answer to this question will be C, 1.60 kg. Now question 5, which will cause vigorous effervescence when added to aqueous sodium carbonate? And I have 3 options, and we will run through each one of them part by part. Now, reacting with sodium carbonate to give me CO2 gas, the vigorous effervescence should be CO2 gas evolved. So this will mean that my solution is acidic. It can react with carbonate, which is a weak base, to give me my CO2 gas, suggesting to me that my solution has to be acidic. What we will have to do is when you're given aluminum chloride, magnesium chloride, sodium chloride, we will have to consider the reaction of period 3 chlorides with water, involving aqueous solutions, involving all these guys, and see whether which one of them will make the solution acidic, and therefore it can react with sodium carbonate to give me CO2 gas. So this guy is actually purely based on periodicity, what we understand, involving the reactions of period 3 chlorides with water, involving aluminum chloride. Aluminum chloride, we will expect aluminum chloride to be soluble in water to give me my ions in solution, and Al3+, because it has a high charge density, highly polarizing, it is able to hydrolyze water and break OH bond in water to release H+, and therefore if it is involving Al3+ aqueous, we will expect solution to be acidic. pH is equals to 3. Dissociation involving my Al3+ complex, when it is coordinated to water, the dissociation is here. Basically, it's just aluminum surrounded by 6 water. You bring one of the OH bond in water, you form aluminum 5 water, 1 OH minus. Charge of this guy will be a +2, and then you kick out H+. It makes the solution acidic, and therefore it is capable of reacting with sodium carbonate to give me CO2 plus water. So number 1, involving aluminum chloride, we would expect solution to be acidic, should be able to react with sodium carbonate. Now how about magnesium chloride? Now in syllabus, when we consider magnesium chloride, we expect Mg2+ to be able to do the same, whatever Al3+ is capable of doing, because it has high charge density, highly polarizing, hydrolyzed water, release H+, make the solution acidic, involving Al3+. Mg2+, in principle, should be able to do the same, but because the charge density for Mg2+, it is smaller, since it's +2 charge versus +3 charge, it is polarizing enough to hydrolyze water, but because the charge density and polarizing power is weaker as compared to Al3+, the extent of dissociation wouldn't be so great, and therefore involving magnesium chloride aqueous, we will expect this guy to be pH equals to 6. Solution is still acidic, but it doesn't dissociate to give me so many H plus or so much H plus, we will expect this guy to be mildly acidic or slightly acidic. pH is equals to 6. Of course, this will mean that, hey, the solution is acidic, it is pH equals to 6, but is it acidic enough to react with sodium carbonate? So this guy is a question mark, and we wouldn't be able to decide based on what we have here. So later what we will do is we will run through the options and see which one is my best answer. All right. Now, how about sodium chloride? Sodium chloride is the easy one because involving sodium chloride, you just dissolve in water and Na+, because the charge density is very low, so it is not polarizing, cannot hydrolyze water. Sodium chloride is neutral. And if it is neutral, there's no reaction with sodium carbonate. Now, if I run through the options, we know that aluminum chloride, definitely, you'll be able to react with carbonate. Magnesium chloride is a question mark, we don't really know. Sodium chloride, we know that it wouldn't react with sodium carbonate. So if you run through, I know that option number 1 must be there. Option number 3 must not be there. In this case, I will have to reject C and D because we know that sodium chloride doesn't react with sodium carbonate. If I'm only choosing between A and B, then you notice we will have to only accept option A because aluminum chloride is the one that we know that can react with sodium carbonate. So in this case, we realize that magnesium chloride is not capable of reacting with sodium carbonate. If we are not able to deduce that, no problem, because based on the options given, only A will be the correct answer. Now, question 6, we have arsenic and X are adjacent elements in group 15 of the periodic table. X and Y, they are adjacent elements in the same period of the periodic table. Question tells me the electronegativity values for each of these elements. Arsenic is 2.0, X is a little bit bigger, 2.1, Y is a little bit bigger, 2.5. What is the proton number of Y? So we have 4 options, 14, 16, 50, and 52. And we want to identify the element actually. We have to identify the element, and then therefore we can link it to its proton number. Now, this question is a little bit unusual, and of course we have to refer to the periodic table to determine this. Topic under this question is actually under periodicity. So let us take a look at this involving a portion of my periodic table. Now we know that involving electronegativity, the most electronegative element is my fluorine, and as I move away from fluorine, my electronegativity will decrease. I will expect fluorine, oxygen, nitrogen, and so on. When I move towards the left-hand side, electronegativity will drop, and when I go down a group, electronegativity actually will also decrease. Again, the idea is fluorine is the most electronegative element. When I'm moving away from fluorine, your electronegativity will decrease. Arsenic is here, and therefore what I want to do is I want to decide, okay, what is my Y, and from there I can determine the proton number. So let us take a look at this part by part. Okay, idea number 1 is arsenic and X are adjacent elements in group 15 of the periodic table. So meaning that when I look at arsenic, and if I look at X, since X is more electronegative than arsenic, so therefore it should be closer to fluorine, because if I consider if they are adjacent elements in group 15, if they're in the same group, I can either go up or I can go down, correct? I can adjacent element can either be phosphorus or it can be this guy at the bottom, antimony. And since the electronegativity is bigger or it is more electronegative than arsenic, and therefore I have to be shifting up, and I know that X in this case will be phosphorus because it is closer to fluorine, it is more electronegative. So now we are here. Basically, we know that X is equals to phosphorus. The next thing is question tells me that X and Y, they are adjacent elements. That means they're next to each other in the same period in the periodic table. So since if I consider X versus Y, Y is more electronegative than X, it will be even closer to fluorine. And earlier we've already determined that since my X is phosphorus, the element that is even closer to fluorine, I have to shift towards fluorine, and it will be sulfur. So from there, I can conclude Y will be my sulfur. So once I've determined my Y is equivalent to sulfur, then my proton number involving sulfur will be 16. So answer in this case will be B. Proton number for Y, which is sulfur, will be 16. Now question 7, you have shoulder glass is composed of 16% boron oxide, B2O3 by mass, and 84% lead-2 oxide, PbO by mass. Question is asking what is the Pb to B molar ratio in this shoulder glass. We have 4 options. Of course, this topic tested. In this question will be mole concept. And effectively, what we will have to do is we will have to try to determine the number of mole of boron and the number of mole of lead in this sample. Then we just compare the mole ratio and we will be able to solve for this question. Now, since everything is in percentages, let us work with 100 gram. In 100 gram, since percentage mass of B2O3 is 16%, in 100 gram, the mass of this guy will be 16 gram, and the mass of lead-2 oxide will be 84 gram. Work based on 100 gram. That is easier for us to calculate. So once we have the mass of B2O3, I can work towards finding the number of mole of boron. Mole of B2O3 will be mass over molar mass, 0.2298 moles of B2O3. In 1 mole of B2O3, I have 2 boron. So mole of boron will be 2 times number of mole of B2O3, which is this value here, 0.4597. So far so good. And we're going to do the same for lead oxide. Moles of lead oxide, mass divided by molar mass, will be 0.3763. Then in 1 lead oxide, there's only 1 lead. So mole of Pb is equals to 0.3763. So once we have the number of mole of Pb and the number of mole of B, I can find the mole ratio between them. Number of mole of Pb to mole of B is 0.3763 over 0.4597. I'll get this value 0.818. So if you run through the options, answer is to 2 decimal places. The correct answer in this case will be A, 0.82. Question 8, what we have is G, H, J, M are 4 elements, of which 2 of them are in group 15, 2 of them are in group 16 of the periodic table. 2 of the elements are in period 3, 2 of them are in the 4th period. The question also adds on to say that the 6th ionization energy values, that means removing electron number 6, of the 4 elements increases from G to H to J to M. Question is asking which element is in group 16 of the 3rd period in the periodic table. So this question is a little bit interesting and takes a while for us to figure out. Topic tested in this question is under atomic structure, so let's take a look at that. Now, first thing is, we know that question is telling me there are 4 elements, 2 in group 15, 2 in group 16, and 2 of them are in period 3, 2 of them are in period 4. So basically, we actually know these 4 elements, or we're able to identify my 4 elements. It will be phosphorus, sulfur, arsenic, selenium, involving period 3, period 4, group 15, group 16. So I've just isolated them. I know that one of them is G, one of them is H, one of them is J, one of them is M. Now, which one is which one? We have to determine, correct? And the next thing we have to take note of is ionization energy number 6. Now, 6, i.e., ionization energy number 6 is to remove electron number 6, remove my 6th electron. And in terms of equation, we will write out in this way. 6th IE is M5 plus, because I removed the prior 5 electron, to give me M6 plus electron. And what we can do for each of these element, we want to write out the electronic configuration for M5 plus, and I consider where is the position of the electron number 6 that I'm removing if I consider ionization energy number 6. So the electronic configuration for M5 plus for each of these elements is here. Phosphorus 5 plus, which has only 10 electron. Electronic configuration 1s2, 2s2, 2p6. Sulfur 5 plus with 11 electrons. Electronic configuration 1s2, 2s2, 2p6, 3s1. Involving arsenic. Actually, arsenic is interesting. If I write out electronic configuration for arsenic 5 plus, I shouldn't be filling up 28 electrons. I actually need to fill up 33 electrons, then I remove 5 electrons. Because if I fill up 28 electrons, then the electronic configuration will turn out to be 3d8,4s2, which is not the correct electronic configuration. Remember, when I write out electronic configuration for cations, especially when it crosses over the 3d and 4s subshell, what we will need to do is we need to fill up the electrons, then I remove the electron from right to left. Because involving 3d and 4s, we know that when we fill up electrons and when we remove electron, there's a switch in terms of the energy level between my 4s and 3d electron. Add electrons to 4s first, when it is empty, when the subshells are empty, but when I remove electrons from 4s first, because there's a change in the energy level between 4s and 3d subshell. So it makes it a little bit troublesome. So what we have to keep in mind is when I write out electronic configurations where the number of electrons exceed 20 electrons, where electron is added to my 3d subshell, then I'll have to fill up the electrons for my atom when neutral, then I remove the electrons from right to left. So the electronic configuration for arsenic will be this: 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p3 for 33 electrons. Then I remove 5 electrons from 4p and 4s subshell. Arsenic 5 plus electronic configuration will be ending with 3d10, involving your selenium 5 plus. It will be 1s2, 2s2, 3p6, 3s2, 3p6, 3d10, 4s1. So we already have electronic configuration for your +5 charge ion for each one of them. Then the next thing we consider is for each one of them, where do I remove your electron number 6? For phosphorus, I'm removing electron number 6 from 2p subshell. Sulfur, electron number 6, I'm removing from 3s subshell. Involving arsenic, I'm removing electron from 3d subshell. Selenium, I'm removing electron from 4s subshell. So we can do comparison already. Let's take a look at that. Involving phosphorus, since electron number 6 is removed from second principal quantum shell, n equals to 2, as compared to the rest of them, sulfur is from n equals to 3. Your arsenic also is from n equals to 3. Selenium is from n equals to 4. So we actually have this comparison already. For phosphorus, electron number 6 is removed from n equals to 2, which is the closest to the nucleus. Attraction is the strongest, hardest for me to remove. We will expect the ionization energy for P to be the highest for my 6th ionization energy, because it is the closest to the nucleus. Attraction, it is the strongest, hardest for me to remove. Now conversely, if I look at selenium, because the electron I'm removing is from n equals to 4, out of all these 4 guys, it is furthest away from the nucleus, easiest for me to remove. Electron number 6, it is the easiest to remove. The 6th IE for selenium should be the lowest. Now, comparing sulfur versus arsenic, what we will have to do is, since both of them, you notice, for arsenic, removing electron from 3D, involving sulfur, I'm removing electron from 3s, and they're in the same principal quantum shell. So what we will do is we will use back the default concept involving ionization energy across the period. The comparison is shown here. Electron number 6 for both of them, I'm removing from the third principal quantum shell. So we will use back the general idea. If I compare arsenic versus sulfur, arsenic has more protons, so nuclear charge is greater. I'm removing electron from the same shell, and therefore the shielding effect is similar. We will expect effective nuclear charge for arsenic to be greater, and therefore we will expect my 6th ionization energy for arsenic to be greater than sulfur. So involving my 6th ionization energy, I'll expect the trend to be here. Selenium, it is the lowest, followed by sulfur, followed by arsenic, followed by phosphorus. And therefore, if I compare this with my elements G, H, J, M, selenium will be G, sulfur will be H, arsenic will be J, phosphorus will be M. So finally, the question is asking which element is in group 16 of the third period. Group 16 of the third period, if you take a look at it, group 16 of the third period will just be sulfur. So basically, it's just a long-winded way of asking you which of these guys is sulfur. We've already identified my sulfur. Sulfur should be H. Answer to this question will be B. Next, let's take a look at question 9. What is the order of decreasing enthalpy change for the 3 reactions shown? We have cesium plus, plug out 1 electron to form cesium 2 plus electron. I minus, plug out 1 electron to form iodine plus electron. And we have xenon, plug out 1 electron to form Xe plus electron. You notice what we are doing for all these 3 processes is I'm just removing the electron from the species, and therefore this is linked to ionization energy. It's equivalent to energy required for me to remove 1 electron from each of these species. Again, the topic tested in this question will be under atomic structure. Now, again, once we recognize that each one of them is just involving ionization energy, so therefore the concept will again go back to the default concept involving effective nuclear charge. If we refer to the periodic table, we notice that all these guys, they are consecutive elements. Iodine, proton number is 53, xenon is 54, and cesium is 55. So it turns out that they actually have the same number of electrons. All of them, they'll have 54 electrons. and therefore the shielding effect is effectively the same. So we can just compare effective nuclear charge, and we consider the effective nuclear charge involving these three species, and we can link it to my ionization energy. So if I consider I minus Xe Cs plus, the proton number goes up, nuclear charge increases, same number of electrons, shielding effect is the same. We will expect as I move across these three guys, effective nuclear charge increases, stronger attraction between nucleus and the valence electron, my IE will go up. So in this case, I'll expect ionization energy for Cs plus to be the biggest as compared to ionization energy for Xe, as compared to IE for I minus. And if you try to rank this accordingly to each of these equations, the ionization energy for Cs plus is enthalpy change for reaction number 1. Xenon is enthalpy change for reaction number 3. I minus is enthalpy change for reaction number 2. So the ranking in decreasing magnitude will be number 1, followed by number 3, followed by number 2. Then if you run through my options A, B, C, D, answer for this question will be option B. Next, let's move on to question 10. Which solid has the most exothermic lattice energy, assuming lattice structure for all the salts is identical? So this question is fairly simple. Topic tested is under chemical bonding. And if we talk about lattice energy, then of course we will have to bring in this idea. Lattice energy is proportional to Q plus Q minus charge of cation multiplied by charge of anion divided by the radius of cation plus the radius of my anion. Charges we can figure out based on information given in the question. The ions we can determine, the charges no problem. The next thing we will have to figure out, or we have to pull from the data booklet, will be the ionic radii for all these species, which I've already indicated here. Ca2 plus, nickel 2 plus, lead 2 plus, zinc 2 plus. The ionic radii is here. It's inside the data booklet, we can refer to that. Br minus, Cl minus, it is stated here. Now, once we compare all the species, we will also realize that all of them, the charge of the cation, they're all plus 2 charge. Charge of the anion is all minus 1 charge. And therefore, what we should focus on is just purely based on R plus plus R minus term. So what I'm doing here is I just consider what is the R plus plus R minus term for calcium bromide, nickel bromide, lead chloride, zinc chloride. So you notice I just add the two values together. The R plus plus R minus term for A, calcium bromide, will be here, 0.294 nanometer. Involving option B, nickel bromide, the R plus plus R minus term will be 0.264 nanometer. Involving lead chloride, it will be 0.301 nanometer. Zinc chloride will be 0.255 nanometer. If I want the biggest lattice energy, then what I will want is I will want the smallest R plus plus R minus term, because it is in the denominator. If there's a smaller R plus plus R minus term, then this will give me a bigger lattice energy magnitude. So out of these four guys, I'm going to choose the one with the smallest R plus plus R minus term, which of course will be zinc chloride. So in this case, answer will be option D.